Okay, we are going to talk about linear functions now. And hopefully this feels really familiar. I think you've been working with linear functions for a long time, so this section should not be too tough. So let's just start with a real life example. We've got maglev trains in Shanghai, and they maintain a constant speed of 83 meters per second for a period of time once it's 250 meters from the station. So it takes 250 meters to get up to speed, and then it maintains that constant speed. Okay, so let's think about how we could represent this. Let's use words first. We could say the train's distance from the station is a function of the time during which the train moves at a constant speed plus its original distance from the station when it began moving at a constant speed. Right? That's a pretty good restatement of the situation. Okay, and we could represent this in a bunch of different ways. We could use equations, right? We could use a linear equation, which has this form y equals mx plus b. We often say it that way, but using function notation or equation notation, we could write it as f of x equals mx plus b, right? Where our input is going to be the time and the output will be the distance from the station. And we could, for this particular problem, we could write it like this. The distance as a function of time is 83 times number of seconds plus 250, right? Once it's 250 meters from the station, this describes its relationship, the distance from the station as a function of time. If we put it in table form, it could look like this. Here's our time, 0, 1, 2, 3 seconds. And our distance from the station, we start at 250, and there's 83 meters. It increases by 83 meters for every second, right? There's a constant intervals in this line of the table, and there are constant intervals in this line of the table, right? These are increasing by 83 each time. And if we graphed it, it would look something like this, right? It would be a line with a constant slope, in this case, a positive slope because the distance is increasing, right? And it would, at time 0, it's 250 meters from the station. So hopefully all of this is looking pretty familiar. All right, so the definition of a linear function, it's a function whose graph is a line, and they can be written in the slope-intercept form like this, f of x equals mx plus b, where b is the initial starting value of the function, and m is the constant rate of change or the slope of the function, right? And the y-intercept happens at 0b, right? When x is 0, y is b. And the graphs could look one of three ways. They could be increasing, decreasing, or constant, right? So the difference between those three cases is the slope of our line, right? So the slope of a function is calculated by the change in y, right? Sometimes you write it like this with a delta, this little triangle, we say delta y divided by the change in x, or delta x, right? Delta y over delta x, change in y over change in x. So if we have 2 points, x1, y1, and x2, y2, it doesn't matter which we call 1 and which we call 2. We just have to be consistent, right? So in this case, let's call this one our first point and this one our second. It's going to be the change in y, so y2 minus y1, over x2 minus x1. Okay, so it'll be the change in y, rise, over run. That's another way we sometimes say rise over run, right? And this is really the same thing, just being stated again. And we usually use the m to denote the slope. Why we use m, I don't know. Maybe it's like a word in Latin that starts with m that means slope or something. Probably a good story there, but I don't know it. Okay, so if we have a linear function and they tell us 2 points and they want us to find the slope and tell us, is this function increasing or decreasing? You could try it real quick. You could probably even try it just in your head. Pause the video, and then there we go. It's going to be the change in output over the change in input, or y2 minus y1, 1 minus negative 2, over change in x, 8 minus 3. So again, negative signs are probably the one thing that can be tricky here. Got to be sure you don't forget the negative signs. And we end up with a slope of 3/5. So is this going to be positive, or is it increasing or decreasing? Well, it's increasing. It's less than 1, but that's okay. We only care if it's positive or negative, right? We're going to go up 3 over 5 for every, to find the slope, right? To find 2 different points. All right, we could have a word problem. The population of a city increased from 23,400 to 27,800 between 2008 and 2012. Find the change of population per year if we assume that it was constant. Okay. Well, what's our input? What's our output? Our input is almost always time. So our input's going to be years, and our output's going to be the population, right? So we could find the change in population, or the change in Y is 27,800 minus 23,400. We get this number. So our change in Y is 4,400 people over our change in X is 4 years, right? 2012 minus 2008, which we can simplify. The population is growing by about 1,100 people per year. Okay, so there's a different form of linear equations called the point slope form. It's just a different way of writing it. It's y minus y1 equals m over x minus x1. And I'm going to tell you a secret. I personally still don't really remember this equation, and I never use it. I just remember y equals mx plus b. I'm not super good at remembering equations, and you can always find what you need just remembering that one, so I just use that one. If you love this equation, there are times where it is more convenient to just use this equation. So if you like to use this equation, you are more than welcome to use it. I'll never ask you to state the point slope form of linear equation, okay? You can use it to solve problems, fantastic. You can always use y equals mx plus b, that's also fine. So I kind of just ignore this, but if you like to use it, more power to you.